genuinely committed into the development of this market. The first one I would name, because it is very clearly mandated by his government, is KOGAS. In Korea, it has been the one that is positioned to develop this industry and the supply chain. But I think it's almost at the same level with Sinopec. JXTG has been an early mover in Japan, and this is very important. On top of this, Asia has been quite strong at developing very effective projects and mechanism to deploy hydrogen stations and to fund this hydrogen station. There is in Japan a very big public-private consortium called Japan Hydrogen Mobility, which is very sophisticated. You'll see after what it is delivering, and similarly HyNet in Korea. And last, Pacific is very, very likely the place where we'll see the first export, overseas trading of clean energy, and that will be another accelerator. So all the conditions are really here to see a lot of things happening in Asia Pacific. If we take a look at Japan's situation, so within this 1.5 billion I mentioned, it is Japan which is the most heavily subsidizing the sector. By the way, for 15 years. So any country which is coming into play needs to have this a bit in mind. So of course, all the ones which are coming after leapfrogging will enjoy a lot of the lessons learned and pre-development, but it's a long-lasting support from the government. They have confirmed and even increased a bit their targets of deployment. For example, for cars, shooting for 200,000 cars in 2025. It's not yet, of course, what we see. I was talking about challenges. Today we can regret that the number of vehicles is still limited, 4,000 vehicles. You'll see in a second that, by the way, in the last few months, Korea has taken over Japan as far as number of vehicles. There is a simple reason for this. Toyota had kind of this plan until the Mirai 2 is launched at the end of this year. It's going to be a big boost in manufacturing capacity, going from 3,000 to 30,000 cars a year. That will go primarily in California and Japan. So we will see an acceleration next year. But we need in Japan on the vehicle side to see much more development of commercial vehicles like delivery trucks that are already in China, or buses. On the station side, so this is a country where there are the highest number of stations worldwide. To date, 120 in operation, 20 completed in the next few weeks. We'll be at 180 by 2022, so it's a good start. But we are working already actively on the financing of the next phase. The next 300 stations are going to be critical. These are the ones that will fully de-risk these markets or not. So very important to look at this. I mean, with a very dedicated focus. There are not so many players these days that are excited about investing money-losing stations. But if you look the full chain, many of the investments that are going to be made in Australia need this success in these countries, Japan and Korea, on the station. So we should all have a very close look to this, and as much as possible contribute to it. In Korea, so without going into the detail, but 1 year ago, the government released a very aggressive roadmap. There is, I would say, the Korean way. There is a very strong intention to develop a big leadership, some national champions in the next decades, and Hyundai is fully leveraging this opportunity. Hyundai will probably have the opportunity to get up into the top OEMs in the years to come, thanks to these developments for cars and, by the way, for commercial vehicles. There has been a drastic acceleration over the last year, so 5,500 cars, 33 stations in operation, 30 under construction. And actually the budget of the government is increasing year on year, so doubling. And this year it will help financing 10,000 vehicles. So basically the subsidy per vehicle is something like $25,000, so significant. Almost 200 buses, which is a start. The target in 2022 is 2,000 buses, and to subsidize, also support the stations build-up. So as any roadmap, the early figures are probably a little bit aggressive. By experience, being able to build almost 300 stations in 2-3 years is going to be a challenge, but they should not be very far from there, so which is very interesting. In China, I'll go very quickly because I think that will be a topic of focus after. We see a lot of these, so it's a market fully geared towards commercial vehicles, buses, trucks of different sizes. Around 2,000 vehicles altogether on the road these days, which is a very strong sign. So probably same thing, not as high as the many press releases we saw around 2017-18, but that's fine. I mean, it's like in any other places, there has been some struggle to initiate the station deployments, permitting issues and so on. We've got some large state-owned companies which are coming into play with Sinopec, for example. And these people are able to accelerate this kind of deployments. We're working with them. That's a station that we opened recently in Zhejiang in Shanghai suburbs. So the goal of the government is around 1,000 stations by 2030. It requires some strong support from the government. There is a bit of uncertainty these days on the subsidy program, the same way that it is being progressively phased out for battery vehicles. So hydrogen from the beginning, the plan has been that it would take over, but the exact mechanism and amounts remain to be confirmed. So when you sum up all this creates some actually quite significant market potential by 2030. If we look actually mobility, so I did not mention the potential volumes of hydrogen in 2030. What we foresee is that China would be clearly the blockbuster, not due to the traditional reason for China, not only this, but the fact that commercial vehicles will be very strong there. Commercial vehicles do consume more hydrogen. So we see in China probably around 2,500 tons per day of hydrogen in 2030. Could be 1,000 in Korea and around 500 for Japan, for the simple reason that commercial vehicle roadmap will be a bit delayed compared to other countries. So mobility alone, we're talking about a market of around 10 billion euro. These are the potential ramp up in these countries, B2B for commercial mobility, B2C. It is an exponential curve. We don't see it yet because the tipping point will be in the following decade. But what we see is that we don't need to wait 2028 or 2029 to see these figures. It's going to be a solid, progressive build-up, and by 2025 there will be already massive volumes. When you complement this with what's coming into other areas, thinking about industry, so conversion of gray hydrogen to green hydrogen in ammonia, in steelmaking, in refining, CCU in a number of processes as CO2. We're discussing with some people before the event. CCS is maybe questionable. CCU could be a solution if we're able to also find a viable business case for this. And energy, whether it's for grid injection or buffering. So all together, just in Asia, and when I say in Asia, I'm talking mainly on the basis of these three countries. Then there could be an entrainment effect that we believe in places like Singapore, typically Southeast Asia, but we're already at 30 billion euro which is absolutely significant. And for a country like Australia, when I was asking the question when, this means that the plans that have been announced since the beginning, from our perspective, are totally realistic, having some exports starting in the window around, let's say, 2028. Makes a lot of sense. As with the pilot countries for export, that would be Japan and Korea. It's not Australia won't be able to enjoy the Chinese market, which will have everything they need as far as hydrogen and even clean hydrogen if when they switch to it. But there is a but, because otherwise all these stories are nice, but there are a number of things that need to be put in place so that it works out. So this is a drawing that has been used by AIE in this study I mentioned, released last year. It was, I think, a nice didactic way of showing what are the big areas of use of hydrogen in the future and of production and the interactions, because this cross-sector coupling is very important also in the value that hydrogen brings. Hydrogen is absolutely a systemic solution, and that's where you kind of unleash all its potential at this point of time. But for all this to happen, let's be very clear, and at least this is Air Liquide's opinion, mobility markets needs to succeed first. If for whatever reason, in 5-7 years, we're still struggling on the takeoff of hydrogen mobility markets, I think it's going to delay everything. There could be some isolated ammonia project and so on, but it will not scale. And so if you drill down one step further, what is needed to make mobility market take off? It is infrastructure. So this station infrastructure investment is critical. And we're working actively with a number of our peers to see what are the right investment models in a number of countries. In some countries where, like typically China, I think it will probably be a no subject. And that's the beauty of the way the economy is run in China. In other countries where market forces apply differently, it could be a challenge. And I think we all need to be very, again, very cautious about this. Once this one is going to pick up, the next booster is going to be the availability of cost-effective hydrogen delivered to this mobility market. And that's when all these industrial hubs are going to develop. We're going to see more and more hydrogen. So there is already a lot of hydrogen in general in industrial basins, refineries, steel making. In a number of cases, it's going to be used, by the way, for this mobility market. But there will be additional capacities, additional ways of delivering hydrogen, typically through liquid hydrogen also, which will be critical. And so that will be the second part, so that we're able to reach a TCO level, and I will come after this, which is compatible with all these applications, especially when you talk about commercial mobility. You won't have massive fleets of buses or delivery trucks if you're not at the right TCO, same level as incumbent technologies. And from there, you'll be able to have all this activation of complementary part of the system, so international trade through exports of clean hydrogen in particular, more and more impact of the connection to grids, the role, the injection into natural gas grid, the role of support to electricity grid. Going very quickly to a recent study that was released by the Hydrogen Council and McKinsey about cost, because we're talking about cost. Again, it can be a kind of a mirage. This is an extensive study done by 60 companies, 25,000 data points that have been injected. And what it shows is that the cost reduction curve by 2030 is going to be massive. Just here an example on FCEV versus BEV by 2025, especially on heavy-duty fleets, it will be competitive, and for others, it will join by 2030. And these will be effects of scale throughout the full value chain. scale on electrolyzer technologies, on manufacturing capacities, on change towards higher capacity distribution systems, progressively pipeline, for example, manufacturing capacities of fuel cell also. So you see the impact of each of these blocks, and at the end, the overall cost, the TCO really of the full solution, will be divided by a factor of 2 over the decade. So this means that a number of applications, each tag here is a given market segment, so either a segment of mobility or some industrial or energy segments. All these blue tags are areas where hydrogen is going to become the most competitive solution by 2030. So this report, I encourage you to go through it. It's downloadable on the Hydrogen Council, McKinsey sites. Very instructive. What is important still is to understand that, again, it will not happen just through magics. There are a lot of investment behind this. All this is supposed to represent about 250 billion of investment, which are not just as such bankable. In order to make them bankable for a number of companies, there will be additional support which is required. Can be early investment of some financial entities, can be government support at early stage, and through this we'll be able to reach the break-even sizes, so around 70 gigawatt for electrolysis, 3 million vehicles of 3 million FCEVs, 20,000 stations. All these volumes, when you look at the scale of energy systems and markets today, are ridiculously small actually. But once we will reach them, industry will be already at the targeted cost. I have 5 minutes probably? 1 minute, so I really need to speed up. That's bad because that's when I was going to speak about my company. So you say I'm a very bad salesman. No, just to say that what I showed before, especially the study, was a bit theoretical. What is real is companies that walk the talk. Air Liquide, we've been investing very heavily over the last few years across the globe to make these mobility markets taking off. A lot in stations initially, Germany, Japan, Korea, and more into some key technologies and production plants. For us, the key technologies we see in the future are electrolysis, very, very clearly. So this is why we invested into this Canadian company called Hydrogenics, and that we are currently building the largest electrolyzer worldwide, a 20 megawatt plant in Quebec. And liquefaction. We are a very strong believer of liquefaction for mobility markets. And so we invested the largest plant ever dedicated to mobility markets to supply the California markets, just allowing to provide competitive hydrogen in this market for the first 50,000 cars. And it was becoming urgent to make this investment because there were not enough hydrogen available for these markets in California. So this shows, again, here the traction that needs to be put. So just to close, so the clock is ticking. We've got reminders of this, I think, every day around the globe. You had it recently with these bushfires. This climate emergency is surely driving a very, very profound transformation of these energy markets. I think by now, even the major energy companies have fully acknowledged it. For Australia, it's obviously the opportunity for a new wave of investment and success. But what is key is that Australia needs to act now. Investment needs to be actively developed and made in the next really couple years at public and private level. There is a very fierce competition for the export of clean energy. Players from the Middle East are trying to find ways to monetize their energy assets there. So typically Saudi Aramco is harassing these days Japan, Korea also to provide their clean energy with different schemes, by the way, than the one developed by Australia. So it's time to move. Thank you very much.
Thank you, Owen. Always a I've heard a lot of hydrogen speakers in my time, and it's always fascinating to hear new perspectives and just how much momentum's really being built up overseas. Let's just hope by, certainly by 2030, that Australia features heavily in the scaling up of pilot projects and the like. Just on formats, we're not taking questions from the floor after each speaker. What we'll do is we'll defer that till the Q&A session when all speakers will have the opportunity to respond to your questions. I will now introduce our second keynote speaker, Alfred Wong, who is the Managing Director of Asia Pacific for Ballard Power Systems, and I'm pretty sure that most people in attendance tonight would be familiar with, it's safely to say, the world's leading fuel cell manufacturer. Been around for a long time, and we're very, very pleased to have Alfred here with us tonight. A little bit about Alfred. He's responsible for the management and oversight of Ballard Power Systems subsidiary and joint venture in China, as well as the development of emerging opportunities in the rest of the APAC region. In his 20 years at Ballard, he's held leadership positions in R&D, technology development, sales, business development and general management. Alfred, it's good to hear, is a licensed professional engineer from Canada and holds a BA, SC and a Master of Engineering degrees in Mechanical Engineering from the University of British Columbia, and also an MBA from Simon Fraser University, and has completed executive training at Stanford University. So please join with me in welcoming Alfred to the stage. All the best.
All right, Alfred, I'm just having some technical issues getting this on the right screen.
Is it true that you guys all heard of Ballard? Or who's not? Okay. Yeah, at Ballard, we're kind of known for being a 40-year-old startup. So we've been in the business for a long time, 40 years. But it's taken this long to really get the industry going. But, I think we're kind of really close to kind of getting to profitability with the rest of the industry. So at Ballard, we have a very simple mission. We deliver fuel cell power for a sustainable planet. It's what we do. We're a fuel cell manufacturer. A lot of what we do is it's on transportation, and I think I'll take you through some of our activities today. But more importantly, I want to talk a little bit more on the industry side, because I think there's really a lot of factors that's kind of driving the momentum. Some of which has already been covered by Erwin a little bit earlier, so we'll probably be skipping through some of the slides. Again, Ballard, we're just by numbers, we're a 40-year-old company, 900 employees now worldwide. Been on the NASDAQ for 25 years. We're celebrating our 28th year on the TSX this year. A lot of our activities has been, again, on the mobility side, buses, trucks, trains, ships, and in forklifts. And a lot of our history has really been around working with automotive companies. So in the early 90s, we were invested by Daimler and Ford Motor Company. Most recently, we have a $80 million development program with Audi. So a lot of kind of our core is from the automotive side, and a lot of our business focus right now is putting that into the transportation and primarily in the heavy duty segment. So I actually want to start where Erwin left off, and that is, if you look at what's really driving the hydrogen story, it's really the climate change story. And if you look at World Economic Forum, the last 4 years, climate change has been on top of the list. This year, in 2020, it's the first time where the top 5 risks are all environment related. And people are starting to recognize that hydrogen really has a role to play here. And interestingly, the word of the year for last year was actually climate emergency. Right, this is, I think we're all familiar, and everyone in Australia with the wildfires. I think this is a theme that we can all relate to, and time of the year, person of the year in time, Greta Thunberg, first time I think we're an environmentalist, has received this award. So a lot of focus being put into this sector due to some very important subjects. Erwin already introduced the Hydrogen Council. If you're not familiar with the Hydrogen Council, I do strongly recommend that you look it up online. Lots of resources about hydrogen and where things are going. Started 3 years ago in Davos, and in this third anniversary, the big theme that's being put together now, it's that this really is the decade of hydrogen. That's where most experts believe that this is really the year that we're going to be making the energy transition out of fossils. I'm going to talk a little bit about that. So if there's really one thing that I can convey here, and if you're not going to remember anything else that I say, I just hope you can remember this. I think that change is going to happen faster than most of us believe. I remember I was at a show last week where somebody said, most people get the path of change correct. So we know that we're kind of heading in that direction. But most people get the pace of change wrong. And this is a topic that I spent a lot of time talking to Randy with, our CEO, who's kind of led the solar industry. And nobody in the solar industry predicted the rate of growth, and also in the battery industry. And I think we're going to see the same thing emerge here. The Hydrogen Council report talks a little bit about it. I'm going to cover a bit of the slides, but again, I think this is a really important theme as we move forward. So the momentum for hydrogen is really increasing, and that's due to a number of factors summarized here. The push for lower carbon emissions, the falling costs of renewables, strategic roadmaps, and also alliances coming together. So Hydrogen Council has been a big part of that, and we're seeing more and more partnerships coming together, and I've got some examples on that as well. So actually, I can't remember who I was talking to earlier about COP26, UK announced, John mentioned that Boris Johnson announced that they're going to pull ahead the elimination of fossil fuel vehicles by 7 years? 5 years to 2035. So we've kind of been in this theme for quite a while, right? A lot of governments been talking about trying to eliminate fossil fuels and putting bans on road, and now we're starting to see more and more getting pulled forward because of the emergence of new technologies like hydrogen. So in the EU, we've seen that in trucks as well. The Class 8 trucks, there's been regulation set that requires the emissions to be reduced by 30% in 2030, a major step towards that initiative. And we're seeing OEMs as well kind of connect to this. Daimler, for example, said they want to be carbon neutral by 2039, and they're now revamping a lot of their product portfolio to try to achieve this, primarily with battery electric and with hydrogen electric. And if you look at some of the partnerships, at Ballard, we've had last year, for those that are following, we've had a big partnership that we announced with Weichai Power, who's the #1 manufacturer of diesel engines in China. We're seeing Bosch partner up with PowerCell, Cummins with Hydrogenics, Toyota, GAC, FAW. So we are seeing more and more collaboration of OEMs with hydrogen companies, with fuel cell companies, a theme that we haven't really seen before. So, and I think as we kind of move forward, we're going to start to see even more of this. Erwin earlier as well mentioned that there are a number of hydrogen roadmaps being put together. Australia just released theirs last year. Now, I believe now there are a total of 18 different hydrogen roadmaps, either through countries or regions that are now coming online that talks about how the hydrogen economy is going to be achieved. And in addition to that, again, this was mentioned earlier as well, the International Energy Agency published this report, which is a really good read, about how hydrogen is going to really play a role in the various different industries. So again, I encourage you to take a look at this. The hydrogen ministry meeting in Tokyo that happened I believe it was in September, where they announced a 10-10-10 plan. So what this is 10 million vehicles, 10 10,000 refueling stations in 10 years. So again, very large scale up that is expected to happen. Now, I think there was a slide earlier that talks about, if we were to get to the, if we're going to get to the goals that we're going to get to in 2030, the 60% cost reduction of hydrogen, there needs to be about $7 billion of $70 billion of investment that needs to happen. Now that might sound like a lot, but I think in the grand scheme of things, on the overall, that really isn't an unachievable amount. So what we're starting to see happen already is we're starting to see an increased investment or divestment out of fossil fuels. I was just talking to John earlier. Maybe you can touch on that. Jacobs left their activities. European Investment Bank just a few months ago said that they're not going to be fueling or funding any fossil fuel investments anymore. That's a very major announcement. And I'm not sure how much coverage this has received in Australia, but this was a massive piece of news in the rest of America and worldwide. Larry Fink from BlackRock, who manages $7 trillion in assets, basically said that they're not going to be putting more money into fossil fuels, and that a fundamental reshaping of finance is about to occur. So I think there are a lot of signs that points that the climate change is really going to change things. We're going to see capital being put into different places, and all of this is really going to help to drive the industry forward. So it's hard to talk about, before we talk about hydrogen vehicles, this is a really key piece to it, to the renewable energy costs, the renewable energy generation costs, and how it's come down. It's really been staggering. So I had some slides on this before, which I pulled up due to time, but if you think about where renewable energy was 5 years ago, 10 years ago, nobody could have predicted that today renewable energy is one of the lowest energy production costs there is, period. More competitive than coal, more competitive to other forms. So if you look at the recent study and look at the levelized cost of energy of wind and solar, it's now competitive on a standalone basis. And I think I was reading a report earlier, the latest PPP project from Dubai. It was 1.6 cents per kilowatt hour. I mean, if you're familiar with this, I mean, this is really, it's really shocking, right? And where we feel this is going is that we feel that renewable energies is really going to hit zero at some point, effectively zero. And that's going to drive a big change in the way that renewable hydrogen is going to get produced. So Hydrogen Council, the latest Hydrogen Council report actually talked a little bit about this. With the fall of renewables, we expect the hydrogen cost to come down as well. 60% reduction is where the where we believe that this is kind of end up, from $6 to about $2.50 a kilogram in U.S. And that's going to really change the economics of transportation and other industries. I believe that many of you may have read about this as well. Siemens-Bach's mega project for green power, one of the largest green hydrogen projects that there is right now. And now moving forward, just now on the transportation, Erwin again teed it up perfectly. For this whole hydrogen economy to work, we think that the transportation is going to be a really core piece. Transportation now is about a third of the energy consumption worldwide. It's got about 20% greenhouse gas emissions comparatively to other industries. So in order to decarbonize transportation, you're going to need hydrogen and fuel cells as part of the mix. There's just no other ways about it. Now, about a month ago, or just recently, less than a month ago, we released a report together with Deloitte to talk about kind of the cost down and what it's going to take to really have hydrogen fuel cell vehicles become mainstream. So not just kind of, as part of, just kind of a niche, but really to be competitive with battery electric and also competitive with ICE. And we think that this can be achieved within 10 years. And, I think, to me, it's kind of it's a conservative estimate. Personally, I think it's going to happen sooner. Again, same slide. If you look at kind of where hydrogen is going to play a role in the various different industries, hydrogen mobility is going to be the most competitive low carbon solution and the most competitive compared to conventional technology. So in heavy duty, medium duty trucks, forklifts, these are the areas that, again, we feel that where hydrogen mobility is going to come first. It's also the area that we've kind of put a lot of focus into as we put our strategy forward. This is a slide that the Hydrogen Council put together that talks about kind of the scale up of hydrogen vehicles. For us at Ballard, we believe that the hydrogen adoption for mobility is going to happen in commercial vehicles first, ahead of passenger vehicles. And that's because if you look at just the barriers to infrastructure, just kind of get centralized refueling, and also the value proposition where if you need to carry heavy payload over long distances, hydrogen is a much better solution than battery electric vehicles. So if there's a sector that's going to go first, it's going to be in the commercial vehicle space. The Hydrogen Council report covers that off quite well. And also as part of the roadmaps that the various countries have put together, there's been a very strong focus as well on mobility sector. Getting to, that talks about how to get to about 1 million vehicles in 2030. So for us at Ballard, a lot of our focus at this time, it's on cost reduction, because that's how we're really going to get there. So and we feel that the cost reduction is really going to accelerate going forward compared to where it has been in the past. So in the past 10 years, we've seen the cost come down quite significantly. The cost of a fuel cell bus about 5-6 years ago used to be about $1 million. It's kind of out of reach for most operators. Now, in 2020, we're about half of that now. In 2023, if we are successful in taking the cost reduction forward, we believe that we can reach total cost of ownership parity with battery electric vehicles. And the ultimate goal is to get to cost parity with diesel, which we think will happen in 2027. So this is based on some of our estimates. The report that's done at Deloitte and Ballard together, we talked a lot about the factors that go into the TCO, including repair costs, fuel costs, maintenance costs. And again, some of our estimates is that within 3 to 5 years that we're going to be reaching that crossover. So in total, in aggregate, there's really a number of areas that we're focusing in to try to drive a 75% cost reduction out of our products. It's going to be done through scale-up. It's going to be done through innovation, but most of it are going to be done with partners. So I mentioned earlier that we've partnered with Weichai Power, with a traditional diesel company, to really look at leveraging supply chain and as well as leveraging some of their manufacturing capabilities. We've got a lot of work that's going on that's more from a design perspective to look at driving cost reduction through process yield improvements and injecting new technologies, as well as considering recycling processes and refurbishing processes in order to really help hold this together. So all in all, these are very, very aggressive cost reductions, but it's really what's necessary to really get us there. Now, what's also important is that as we look into getting cost reduction, that we maintain our same or that we at least maintain the same performance, if not improve on performance. And that's a lot of what we're doing at Ballard is to try to do that, try to get volumes and weight lower, increase operating lifetime, all while we're trying to get costs out of our products. So I just want to close by going through some of our slides on China, which I think it's necessary in order to kind of get the scale of the speed that things are going. It's kind of hard to talk about fuel cells without mentioning China, because I think this is really going to be the area that's going to drive volume and scale, just because it is the #1 EV market globally right now. So about 3 years ago, the total number of fuel cell vehicles in China was about, I think, 50. And now, I think the latest number from the CIIM report, or the CIIM, the Association of Manufacturers, CAAM, sorry, has reached 5,000. So the growth has really been phenomenal, and we've been part of that growth as well. So in Shanghai, 600 logistic truck. I think it was a similar picture that Erwin showed earlier. In Shenzhen, the southern city known as the Silicon Valley of China, we put 500 logistic trucks now on the road. Zhongshan, just about an hour north of it, 100 delivering goods. In Foshan, just about an hour off of Guangzhou, there's now 300 intercity buses running. That's 8.5 meters. Jinan, 40 fuel cell buses, and Laochang, 30. So in total, a lot of these gets missed. I'm not sure how much coverage there is in Australia, probably none, but the adoption is happening. The cities are trying these buses, and we're going to see lots of these getting rolled out. So now, next year and the year after, what's really going to happen is that we're going to be moving from the thousands to the 10,000s, and that's really what we're preparing for over the next 3 years at Ballard, is kind of getting that next level of scale up. Also want to touch on one thing, just looking at some of the trams that's out there in Melbourne from this morning. Just a few months ago, we launched the world's first commercially operating hydrogen-powered fuel cell tram. It's about the first phase of the line is about 10 kilometers long, covering 10 stations. So this is a line where there are no catenary lines. So when the city decided to do the forward planning, they actually didn't put catenary lines on. And when we signed the deal, it was either going to have to work or we were going to really get into a problem. So now, 4 years later, it's now in commercial operations. It's 2 RMB. You can go ride it. You don't need to call me or anybody else. But these technologies now, it's starting to get demonstrated. And I think over the next little while, as people start to catch on about these new technologies, we're going to start to see more and more of these rollouts. I know I'm out of time. I just want to touch on one thing, on a quote by Harvard professor Clayton Christensen. Now, when we talk about disruptive technology, a lot of people always consider that, it's a technology problem. But this really isn't a technology problem from Ballard, and I think most people in the industry. This really should be framed as a marketing challenge. And, it's part of why we're all together. It's really about drawing awareness to the availability to the technology, to how fast it's scaling up. And I think, we can all work together to really try to accelerate this event and really help our Earth. Thank you very much for your attention.
Thank you, Alfred. What a fantastic presentation. Many years ago, people thought even solar PV was beyond reach and a pipe dream. I think when back at Melbourne Uni days, we were looking at costs of 10,000 a watt. Now it's 30 cents. There's no reason to think that couldn't occur in hydrogen technologies. And let's just hope that Australia's not too far away from what's evident in parts of China and Japan, no doubt, and certainly in Europe. So thanks for that. What a fantastic presentation. Thank you, Alfred. Okay, now we get into some local content. and we've deliberately looked for a diversity of input to make this forum as valuable and meaningful and hopefully useful to each and every one of you. And it's with great pleasure that we've partnered with ARUP in coordinating this forum, but also to have Jonathan Anderson join us tonight from ARUP, not only because he's an up-and-coming star of our emerging hydrogen industry, but because he's actually proactively working in real-world projects. And that's the next step beyond national hydrogen strategy and roadmaps, is let's start seeing some real-world projects. Jonathan is a senior, wonderful, engineer, engineering consultant with broad industry experience across renewable energy generation and storage, water and wastewater management, mining, waste, agribusiness, freight and logistics, and process automation. With an increasing focus on the energy transition, he brings this diverse background together with a firm grasp of first principles science and engineering to uncover novel solutions to new problems, and certainly confronted with lots of problems as hydrogen emerges, and we need people that have got solutions. He's one of them. Having been design lead on demonstration hydrogen projects and a contributor on several strategic hydrogen studies, Jonathan brings an informed and fresh perspective to hydrogen's potential role as a tool for decarbonisation in the 21st century. So without further ado, please join me in welcoming Jonathan to the stage. All the best, mate.
Thanks very much. A lot quicker at getting my own slides up. I'm not sure what that's about. Thanks for having me. I'm going to talk a little tonight about learnings that ARUP's had from some projects that we've worked on in the industry in the Australasia region. I'm going to leave behind all of the hydrogen background and context because I think my colleagues here have done that pretty well already. I'm also going to talk a bit about where we get the water and the electricity for hydrogen production by electrolysis and why that matters and what impact it has on projects. And finally, just a little bit about my view of how we might scale up the industry and the barriers that we're facing as we try to do that. I gave a dry run of this presentation at lunchtime to some ARUP people and it took me about half an hour. I think I have about 10 minutes now, so I might just do a keyword per slide and let you fill in the blanks. So lots of people very excited about hydrogen at the moment. That's why we're all here. That includes ARUP and our clients. I've just got a bit of a selection of some of the clients we're working with that I guess give an overview of how broad this industry potentially could be. So Ministry of Business, Innovation and Employment in New Zealand and COAG Energy Council in Australia. We've done strategic work with them, developing the New Zealand Hydrogen Green Paper and the Australian Hydrogen Hubs report that I'll talk a little more about. Kiwi Rail in New Zealand and the Rail Safety and Standards Board in the UK. We're looking with them about the feasibility of hydrogen on the rail network. City of Greater Bendigo looking at whether their contaminated groundwater that's currently an economic drain on the city could be turned into hydrogen and turned into a valuable resource instead. High for Heat, government-funded project in the UK that's looking into the feasibility of hydrogen in the gas network. Engie, we're working with them on whether hydrogen could be used to provide critical services to the power grid. Shell, we're looking at on export opportunities. And Ports of Auckland, I'll also talk more about. We're helping deliver Auckland's first hydrogen refuelling station at the moment. Here are a few, I guess, thought pieces that ARUP has put out into the world, nice shiny documents. I think there's a few of these floating around tonight in hard copy form in case anyone wants to take one home, but also you can find it by Googling ARUP Hydrogen, or I'm happy to send through a copy if you want to get in touch with me. Energy Systems, A View from 2035, basically puts forward some scenarios for what the energy system could look like in the future, establishing a hydrogen economy on the right. Talks about what role hydrogen could and or should play in that future energy system. And then the 5-minute guide to hydrogen, which I love. It's basically it's a kind of a reference slide deck for Hydrogen 101. So it's a really useful little reference tool. So I guess with the topic of this forum being projects, investments and market outlook, before I get into projects, a look at what the sort of different demand growth scenarios that are out there are saying. So this graph is pulled from the Australian National Hydrogen Strategy, which a lot of you have probably seen or read. And we see here the Hydrogen Council, which we've heard mentioned a few times tonight by Alfred and Erwin. They've got a fairly, I would say, an optimistic estimate of what the hydrogen demand globally could be in 2030, and then a bunch of other estimates, some of the more pessimistic ones from the National Hydrogen Strategy, the scenarios where it's business as usual or even electric breakthrough means that we don't need hydrogen the way that we thought we might, and some forecasts from Shell and ASL Allen thrown in there as well. And then for 2050, we see a very bullish forecast by the Hydrogen Council, and I suppose some similarly optimistic forecasts from IRENA, the International Renewable Energy Agency, and the most optimistic scenario from the National Hydrogen Strategy for Australia, and then some less optimistic ones down below. So I suppose this gives a flavour to how nobody really knows for sure how this is all going to play out. And I appreciate that the Hydrogen Council is certainly optimistic. I think they wouldn't want to be pessimistic about it. And I hope that it does develop that way, and I hope it develops that way with zero carbon or low carbon hydrogen. But I think, we've certainly got some barriers to achieving that kind of growth, and some of those barriers are really somewhat outside the control of the people who are trying to build the hydrogen industry. I think there's a lot of technology development that needs to happen to bring costs down, and a lot of government support that needs, and coordinated government support that needs to happen as well. So first of all, I'm just going to talk briefly about the Australian Hydrogen Hub study that we did for the COAG Energy Council, and this fed into the national strategy that was released last year. The idea of this project came out of some work that the International Energy Agency did that suggested that an effective way to scale up the hydrogen industry is to, at least at first, concentrate it into hubs where you can aggregate demand, you can aggregate hydrogen production in places that make sense, where it's cost effective to do so, and you can maybe concentrate it in places that make sense from an export perspective as well. So COAG took that on board and they said, well, someone figure out, please, what kind of places would make sense for hydrogen hubs in Australia, and that was our job. I think this project really built on the work that Geosciences Australia released, which some of you might be familiar with. It was essentially a resources assessment of what regions might make sense for hydrogen production in Australia. So it looked at factors like water availability, quality of energy resource, whether that's renewable resources like solar and wind, or it might be gas reserves or coal. And it looked at connectivity with things like gas transmission and electricity transmission. And it basically created this heat map. And COAG wanted to take this work that had been done and look a bit more holistically about, the other things that you might consider when you're figuring out where a hub should be, like areas of current hydrogen demand, maybe large-scale ammonia production plants or steel making, or other factors as well, like existing ports. So this is the list we came up with of potential hydrogen hub sites. And I don't expect you to read the list, but you'll notice that most of them are ports, and that's not a coincidence. I think hydrogen, it's well recognised that hydrogen export is going to be one of the key opportunities for Australia in the whole picture of what hydrogen could be. And so putting our demand and production hubs near a existing port makes a lot of sense. I think the scope of this project initially was to then do an assessment, a bit of a multi-criteria analysis on which ones of these would make the most sense, and give a bit of a list to COAG saying, here are the ones you should develop further. I suppose COAG as an entity is it's unquestionably political. It's made up of, for anyone who's not aware, the state and federal energy ministers, and depending on what resources a particular state has available, they may have preferences for different hydrogen production pathways, depending on what party is in a particular state. They may have preferences for fossil fuels versus renewables. I'm just speculating. And I think this led to a bit of a political compromise in the delivery of this project, which meant that instead of assessing the sites, we would just develop a framework for how you might assess sites and then hand that over, and the Queensland government could go and sort of assess the sites themselves, and the Victorian government could go and assess the sites themselves. So that's how it sort of played out. I guess in terms of the framework we developed, I won't go into too much detail, but the key factors we propose that you want to consider from a hydrogen-specific perspective. You want access to demand, existing demand if possible, so you want to be close to places that are already using hydrogen, you know, regardless of it being green or not. But it's not. You want to be close to good production regions, so you know that basically where the energy resource is available and is strong. You also want to have the potential for hydrogen storage, so particularly in terms of risk factors associated with storing large volumes of compressed flammable gas, for example, that needs to be considered in siting of these facilities as well. From a utilities perspective, you want to be ideally close to a grid connection, you want to have access to water, you need to have access to gas transmission ideally, whether that's for gas supply, if you're doing steam methane reforming to produce hydrogen, or if it's as a source of demand, so you can inject into the gas grid. And the price of the electricity that you can produce at your given site is very important as well. Land and transport, in terms of the land availability and ownership, that's a critical factor driving siting, and access to transport infrastructure like road, rail and ports is also very important. And finally, I guess broader economic and social and environmental factors are important to consider as well. So the next project, and this is one of the real projects that Lou mentioned. I'm not sure I could call this real yet because there's nothing actually on the ground. So this is the Port of Auckland refuelling station. This is a real life photo of it. So Port of Auckland developing a refuelling station. This is probably one of the most interesting parts of this project for me. You wouldn't normally think of a port as the kind of organisation that wants to build a refuelling station at their site. It's a bit of a curveball. I think this highlights for me how the energy transition, sort of considered broadly, is bringing a lot of new players into the energy market that wouldn't have previously been interested. They don't see it as their game. I think Port of Auckland being driven by a decarbonisation strategy of their own, they want to be zero carbon by 2040. They look at their current operations and they see a whole lot of heavy equipment using diesel. They also see that they're an important part of the freight network in New Zealand, and that whole thing runs on diesel basically. So they want to be leading from their own perspective in decarbonising, and they want to be leading New Zealand's economy in decarbonising as well. And so they see a hydrogen refuelling station as a good starting point for heading through the journey. So we've supported them basically from when this project was a bit of a kernel of an idea. We've helped them through site selection, where on the port would make sense with a multi-criteria assessment, design development, putting together the business case, stakeholder engagement, which has been really important on the project, planning consent and regulatory issues, and yeah, so I suppose the purpose of the project initially, and I think this is another key thing about the hydrogen market broadly that Alfred has touched on, and I think Erwin touched on as well. Partnerships are just critical. Port of Auckland, there's no major pieces of equipment that it can purchase at the moment that makes sense for it that can consume a lot of hydrogen. In order to make this hydrogen refuelling station viable, it needs to be kind of a significant scale. So initially, they've partnered with Auckland Transport, who are going to be running a bus trial at the same time as the hydrogen refuelling demonstration plant is coming online. So that, I think at this stage, it's about 2 to 3 buses, and that'll be about 80 to 100 kilograms of hydrogen per day. it provides the foundation that you can build a broader refuelling station around. In the longer term, Ports of Auckland want to use the extra hydrogen that this can produce and maybe even scale it up to be able to run heavy equipment like their straddle carriers that carry containers around the terminal, also their tugboats, and they may even trial some trucks as well in the near future if they can get their hands on them. And I think in the longer term, the port can see themselves, they own some really key strategic freight hubs in New Zealand, and you know, as we've discussed, commercial vehicles are going to be the ones to probably go first in hydrogen, and one of the big reasons for that is because of the sort of node-to-node or back-to-base transport that that sort of characterises them. And I think ports recognise that they own the hub. They can become the fuel supplier for the freight industry, which provides a really interesting source of business diversification and alternative revenue for someone like a port. So I'm not sure if it will play out that way, or if the energy companies, the traditional energy companies, will come to the party a bit more. But it's certainly it's a really interesting sort of future scenario for the freight industry in New Zealand. The other thing that actually, well, I mentioned partnerships earlier. I think the other partnership that's been really critical on this project has been in terms of overcoming the regulatory hurdles and the planning hurdles, because this is so new in New Zealand, and it's a similar problem in Australia. All of the regulators, all of the planning authorities are still wrapping their heads around how do you make sure that these systems are installed safely in the Australian context, and how do you make sure they're efficient, and how do you make sure they're fair? So Ports of Auckland has taken a collaborative approach. They've engaged with other hydrogen projects in the country, and they've engaged really closely with regulators, with the Ministry of Business, Innovation and Employment, with WorkSafe, with Auckland Council, and they've formed close relationships so that they can work through all of these issues, and there are a lot of them. They can work through them together and come up with solutions that will allow for safe, efficient, fair refuelling projects and hydrogen projects more broadly, without holding up the process and driving away investment. In terms of water supply, so I'm not going to spend too much time on this because I'm conscious that I might step on John's toes, because I think he's going to talk about water in a bit of detail. But just briefly, in terms of water supply for electrolysed hydrogen, it needs about 9 litres of deionised water per kilogram. Unfortunately, deionised water is kind of hard to come by in nature, so whatever source you're starting with, you need to treat it first. That means you normally need to start with around about 15 to 20 litres per kilogram. In terms of the costs of that, so if you think about the cost of potable water, it's usually somewhere in the order of $1 to $5 per kilolitre. If you consider that's about 15 to 20 litres of water per kilogram of hydrogen produced, that comes out to somewhere in the order of 2 to 10 cents per kilogram of hydrogen. We've seen the numbers for how much it costs to produce hydrogen overall. It's in the several dollars range. Currently, it's in the more than tens of dollars range. So we're talking about, at the moment at least, less than 1% of hydrogen production costs. So I guess from a technical and economic perspective, water supply isn't a very significant issue for hydrogen production by electrolysis. But I think from a social perspective, especially in Australia, it's critical. Our freshwater supplies are already stressed, and that's only going to get worse. I think given that the cost is so small, and we have so many alternative water sources that are available that will add very little cost to the hydrogen in the grand scheme of things, we could take an approach of saying only alternative water sources are allowed for producing hydrogen by electrolysis. And that may help in the overall scheme of trying to get a populace that is supportive of a hydrogen economy scale up. It may help achieve a social license. And lastly, I'll just talk about energy supply. So is everyone familiar with the different colours of hydrogen that you can have? Green, blue, grey, brown. So green is produced by electrolysis with renewable energy, zero carbon energy. Blue is coming from traditional fossil fuel sources by coal gasification or steam methane reforming, but with carbon capture. And grey/brown essentially means produced by traditional methods with no carbon capture. So I suppose the one that's missing for me, and the one that's really important to consider when we're thinking about electrolyzed hydrogen, which is the pathway that I'm probably more excited about, is when you're producing hydrogen by electrolysis but with grid electricity. Because it just so happens that Australia's grid is mostly powered by the worst fossil fuel you can possibly get from a carbon perspective, which is brown and black coal. So this next slide is pulled from Australia's National Hydrogen Strategy, and it puts some numbers around what the carbon intensity of hydrogen is, depending on how it's been produced. So we can see there the most common method, steam methane reforming from natural gas with no carbon capture, about 8.5 kilograms of CO2 per kilogram of hydrogen produced. Coal gasification with no carbon capture, 12.7 to 16.8. Electrolysis from 100% renewable energy, 0. Fantastic. Electrolysis from Australian grid electricity, 40.5, which is a lot higher than either of the methods of producing hydrogen directly from those fossil fuels. And that kind of makes sense when you think about it, because there's a lot of energy conversions that need to happen along the way. There's a lot of inefficiency that adds. I do think this is a really important nuance that we need to consider when we're thinking about how to scale up electrolysis production of hydrogen. So just to talk briefly about a couple of different potential scenarios. If we think about powering an electrolyser, actually before that, when you're talking about a hydrogen production by electrolysis project, there's a lot of parameters driving your business case, but the three most important are how much does your electrolyser cost to buy, and that's driven by the output capacity of your electrolyser, kilograms per day or megawatts. The utilisation of your electrolyser, which is, does it run flat chat at full capacity or does it ramp up and down? And the cost of your energy coming in. So we've heard a bit about how solar and renewables in general have fallen very dramatically recently, and they're now at cost parity or even less in terms of levelised cost of electricity with traditional sources. The thing that I think sometimes gets forgotten is that they're not on all the time, and that's a really important thing to consider when you're talking about running a hydrogen electrolyser. So if you wanted to run an electrolyser off solar and just ramp the electrolyser up and down with the solar, you're probably talking about a 20–25% utilisation, depending on your capacity factor of your solar, depending on where it's installed. That ends up meaning that your electrolyser is 4 or 5 times more expensive than it would be if you just ran it flat chat, because you have to oversize it so much. If you want to run it off a solar with a battery, and the battery can store the solar energy overnight so that you don't have to ramp down your electrolyser and you can fully utilise it, your battery needs to be, I think it's about 4 or 5 hours of storage at full capacity. And that, it basically multiplies your project capex by about 3 or 4 times, depending on the type of battery you use. So I guess what I'm getting to here is that it's still very expensive to produce green hydrogen, and it's going to be that way for a little while yet. And we have to I think we have to, while not let that hold this up, we need to understand it and figure out how we want to respond to that. I think there's interesting ways that you can get a greener than usual supply from the grid. You can look at, say, renewable PPAs that maybe allow you to get grid electricity that's somewhat green, but at a cheaper price. But we need to understand that that cheaper price is enabled by all of the fossil fuels that are also feeding into the grid. We can also look at things like carbon credits, maybe, as ways of achieving a greener electricity supply despite the fossil fuel emissions that are coming with it. And hopefully in the long term, we can see capex reductions that Alfred and Erwin are talking about in electrolysers that will mean that the utilisation doesn't matter as much anymore. And that would allow the ramp up and ramp down to sort of be viable. Just really briefly now about where to from here. I think A critical thing to understand about hydrogen's potential role in decarbonising our economy is that there's a lot of different roles that it can play. And for each of those roles, there's a different break-even cost. So as Alfred and Erwin have touched on, it's probably heavy transport that's going to go first. And one of the big reasons for that is that the break-even cost is the most favourable to hydrogen. I think there are other ones that can happen quicker for different reasons. For example, ammonia and refineries, they're already huge consumers of hydrogen. If we can support them financially in purchasing some green hydrogen to offset their traditional hydrogen use, then maybe that's a way of achieving some scale up faster. But it'll require either government incentives or subsidies, or it'll require those businesses themselves being willing to take on that cost in order to achieve the decarbonisation and maybe achieve long-term cost reductions through the scale-up of this technology. I think gas blending is probably another one where we can have some government intervention, putting in mandatory blending targets that will get us starting to walk down the path of scaling up this industry. I'm going to leave it there and hand over to John, and he's going to say everything I got wrong about the water section. Thanks very much.
Thank you, Jonathan. I just might add something in terms of regulatory passage for hydrogen technologies to be scaled up, that Standards Australia has formed a committee. I'm lucky enough to serve on that committee. It's called ME 093, and it's mirroring this International Standards Organisation Technical Committee 197. And basically what's happening there is we're looking at the existing international standards and we're looking to amend them for application within Australia. So I would say within the next 12 to 24 months, there will be no regulatory hurdle, that we'll have codes and standards applicable to all electrolysers, natural gas substitution, electrolysers, storage of hydrogen in gaseous or liquid form. We're even going to the extent of looking at liquid hydrogen transfer arms from a liquefaction plant to a transport ship. So that is a dedicated initiative. We've been calling for it for some time, but we're heading in the right direction. That's certainly going to accelerate the uptake. It's been referred to a number of times through the course of the first three presentations, the pairing across different industries for the uses of hydrogen. And we've specifically sought out our next speaker, John Poon from Jacobs, to illustrate how hydrogen may find application in more than one industry simultaneously. So given that we're behind schedule, I'll just quickly introduce John and then he can explain what Jacobs is doing in this area. I'll get these glasses on. Okay, that's better. John Poon is the Director, People and Places for Asia Pacific for Jacobs. John has over 30 years of experience in water and wastewater engineering. He has completed projects for several Southeast Asian countries, including Singapore, Hong Kong, China, Malaysia and Thailand, as well as the subcontinent India. In Australia, he's managed and designed a broad range of projects for diverse public and private sector clients. John has unique insights and experiences of advanced treatment projects, social acceptance of recycled water and delivery of integrated water management projects. John is a co-author of the Jacobs White Paper, Australia's Pursuit of Large-Scale Hydrogen Economy, which was published in May last year. He led the water and recycled water components. This paper produced many insights into the future role of water utilities in hydrogen economy. He's now leading some of the first projects in the large-scale use of hydrogen by the water industry. Please join with me in welcoming John to the stage. Good luck.
Thanks for the invite to speak tonight, and thanks, Jonathan, for the lead-in. Appreciate that. I'll try not to pick holes. And Erwin and Alfred, thank you very much for that insight into what's happening in the globe, the world, because sometimes I think in Australia we get a little bit insulated. An example of that was today. I was actually at RMIT University for their Engaging for Impact conference, which they hold every year, and I was in the transportation transformation section listening to what they were going to talk about. And I'll mix transportation and mobility together. We kind of use transportation here in Australia. But they are stuck. They were talking about, you know, good things like getting access for people onto the public transport system, drones. I mean, yep, I guess that might be something transformative in transportation. Ford Motor Company was there talking about smart sensors and all that sort of stuff. And I was kind of disappointed because no one really talked about the decarbonisation stuff that we need to do, and what Boris told us today, or yesterday, that he's going to effectively outlaw internal combustion engines from 2035. So let me start with that. So thank you very much for that. But I'm the Technical Director for Drinking Water and Reuse in Jacobs across Asia Pacific. And why is the water guy here? All right, why? So let me just take you through that. And what I'll do though, but bear with me, I've got to do the sales thing first, Erwin. So maybe that's the lesson to learn. Let me get this first bit done. So we've actually decarbonised ourselves as a firm. All right, so Jacobs is traditionally, or legacy business for Jacobs is oil and gas. Okay, that's where we started. But last year we sold it, and we sold it to Worley's. Okay, and it's very interesting to see that Worley's are now getting into renewables. So I thought, well, that's a good sale. So we have effectively got out of it, and we don't believe in it. And we have also rebranded ourselves, and that's where you see the new logo, the Jacobs logo, and you also see our new branding as well in terms of challenging today and reinventing tomorrow. And that's what I'm going to sort of talk about today, because that's what we're really about, is getting solutions to some of these big problems that the world is facing. So let me just move on, because I know we're constrained for time, and I'll do my best to stick on what I've promised to do. But what we're really about, so where I am, I'm in people's, places, solutions, right? It's a bit of a mouthful to say, and I don't know why we picked that, but it does explain what we're sort of all about at Jacobs as well. We're really about cities, okay? Humans living in cities, okay? Because we just passed a milestone a couple of years ago. More than 50% of people now live in an urban setting, all right? First time in human history that's ever happened, okay? And we're projecting it to go up to 70% of people, all right, by whatever date that is, by 2050, all right? There's going to be a lot of us living in city settings, all right? And what really got my attention last year was this article in the National Geographic, and it talked about what does a city need to do to be basically sustainable and be able to meet the challenges of tomorrow. And you can see the keywords there: ecology, water, energy, livable, has to be livable, waste, food, mobility, culture. But I'll just focus on some of the green ones there, all right? We're talking about capturing our wastes, okay? Well, it's no longer waste, right? We're capturing our resources and reusing them. Yeah, all waste is a resource. But see the bottom one there about infrastructures, carbon neutral infrastructure, and probably it might need to go to carbon negative infrastructure as well, because a lot of our water clients are talking like this, right? They have, in Victoria, committed to actually go carbon neutral by 2030, okay? Very few industries I've actually seen, so they're taking a leadership position. So I was in a workshop this week, and we had one of the managing directors of the sort of large water companies in the meeting, and he gave us an address, a 10-minute address, before we did our workshop, and it's very much about this. The water industry wants to build regenerative systems, right? We no longer want to just take the waste or grab the water out of the environment, use it once and just throw it away, okay? We're trying to actually move to something like this. So this is where we are heading at the moment. So last year we released the Melbourne Sewage Strategy, right? We're looking 50 years ahead to what is the Melbourne sewage system going to look like. And we think it's going to change, all right? We think it's going to become, instead of a sewerage system, it's going to become a resource recovery system. And we call it of the future because obviously it's going to be in the future to do that. But we see the current system going from this linear treatment system to a more circular system. Okay, and that's what we're talking about today. So the things that Erwin's talking about and Alfred's talked about, Jonathan's talked about, we are trying to close the resource loops right now because we can't afford to do what we're doing today. Okay, and we've captured that. Melbourne knows that we have to do something like this in the future. Okay? And it's also consistent with the UN SDGs, and basically, yeah, we're actually starting to embed the UN Sustainable Development Goals into our actual planning, what the city may look like. Now, we have a big job ahead of us, all right? I think someone was talking to me today about carbon emissions. It might have been Jonathan Sodenberg. And we are disappointing. We are sadly lagging the world. If you look at our carbon emissions, all right, we say we want to meet targets of 26%, 28%. You can see those in the red dotted lines and the black dotted line there. But the real trajectory is where the blue and the green are. We're not tracking too well on the targets, all right? And you've got to remember the scale on the side there. That scale is not 0 on the bottom axis. All right, it's 300. All right? We're not even close to carbon neutrality. And we're not even tracking down. It's pretty sad when you look at that. Okay? So hence why it's really important that we start to look at what we're talking about here when Erwin and Alfred have been talking about. And yes, there's a lot of roadmaps out there, and we've got the latest one out there in the bottom hand corner here, which is the Australian National Hydrogen Strategy, which Alan Finkel launched in December last year. And we also have Queensland and other states are also coming up with their roadmaps as well. And as I think you're talking about the chemical industry, we've got a real issue there in the chemical industry. Right? They're not pulling, well, basically not pulling their weight. Because when we look at who are the major carbon emissions in the world, global emissions, well, chemical industry is about 30% of it, right? It's an essential part of our economies, but it's 30% of it. And I think someone today, I can't remember who it was, might have been Erwin or Alfred, steam methane reforming for ammonia production, look at that. Yeah, I think it might have been Jonathan or whatever. 9 tonnes of CO2 is generated for every tonne of hydrogen. It's just enormous, all right? And that's for ammonia production, explosives productions, all the things Australia wants to do. All right? We need explosives for mining. We need fertilisers for agriculture. And look at all the other industries as well. So the adipic acid plant, which is basically making plastics, the monomers for plastics, very energy intensive, but also very carbon intensive, and also the steam crackers that are in many oil refineries there as well. So we need solutions around this because, speaking for me, and sorry it's a little bit small to see, but if you see the red line at the bottom there, the waste industry, okay, wastewater treatment is about 2% of the world's, you wouldn't believe it, would you? We're 2%. Our wastewater treatment systems are 2% of the global emissions in the world. It's incredible for treating your waste, okay? And this is where it brings us to what the interest of the water industry is in this area. So I come across to the hydrogen economy white paper that we issued, and you're welcome to go and get it. There's a video that goes with it as well. Apparently it's a good read from what people tell me. Yeah, we had some excellent feedback on it, and it's certainly changed how people think what Jacobs is, which was, I guess, some of the purpose of doing that as well. But it was a true cross-sector collaboration across all the things that Jacobs can do: transportation, mobility, power, strategic consulting, okay, the energy, the water, and the marketing as well. So we actually got the marketing covered as well, so disruption marketing. So we've covered it. If you haven't read it yet, have a good read. I'm going to give you a bit of an insight into what it covered as well. But how did this start, this paper? Because Jacobs, up until this point, is pretty much not featuring in the hydrogen world at all. How it started was the strategic consulting guys, our energy guys, came in and said to me one day, hey guys, hey John, we're actually looking at using hydrogen in transportation, mainly rail. Okay, and I said, oh, that's a great idea. Really good. Yeah, wonderful. But how do you get in the water? Oh, you know, we just get it from the tap. And convert it. Oh, gee, I said, well, Australia, Jonathan, Australia might be a little bit of a problem just grabbing stuff from the tap all the time. Okay? And so that's where it started. So we said, let's look at this a little bit deeper. And we got pretty deep. So this is how the sort of current model is for green hydrogen. Well, that's what we looked at anyway in terms of business as usual. Let's take the energy from the grid. Let's take the water from the drinking water system, put it into an electrolyser and then store it, use it. Okay? Standard stuff, and I won't dwell on it. Then we said, well, let's look at this. How do we do green hydrogen? And I actually call it sustainable hydrogen because what we're doing now is the energy is actually from renewable generation. So I like to change the colours. No more colours now. I'll just call it sustainable hydrogen. And we actually get the water from recycled water. Well, why recycled water? It's only 1% of the cost, right? Jonathan said that. And that's what the equipment manufacturers told me as well. They said, why, John, why are you focusing on this for so much? I mean, you're so obsessed with water. I said, well, I'm the water guy. What do you expect? But really, when you look at a big city like Melbourne, I hold my head in shame because we only do about 5% water recycling in the city of Melbourne. It's a shocker, isn't it? Go and have a look in the annual reports for Melbourne Water. It's not good reading. And I would say it teeters on the point of maybe a bit misleading as well, because I had to take the padding out. They have a lot of padding numbers in there. But if you take the padding out, get down to what's true recycling, it's 5%. They push it up to 15, but I say, oh, dear, a bit iffy. Some of those numbers, sprinkling on the ground, I don't call that recycling. Yeah, all right. But that's where we got to. So we looked at that model as well. And what we did was we said, well, rather than talk about it in, so helicopter views and all that sort of stuff, and very big macro looks at things, let's zoom down into something which is pretty important in Australia. How do we transport stuff around Australia? All right, because I don't know whether you know this or not, but transportation or mobility in Australia, 20% of our carbon footprint is actually in the transport sector. And it's the sector that hasn't done a lot of work in decarbonising. It's pretty sad. Not only are we holding our heads in shame for recycled water, but we're holding our heads in our transportation sector. It's pretty sad when you think about it. Okay, so how do we do it? Well, so this was the test case that we put through there. Let's look at the rail corridor between Perth and Melbourne. It's a pretty long distance. I think it's about 3,000 k's or something like that, and uses up quite a lot of diesel fuel to actually run it. And we looked at a number of scenarios. I'll let you guys read all that, but it's scenario 3 that really interested us around the sustainable hydrogen supply chain. And we looked at using, obviously recycled water and renewable energy to do that. And we looked at sort of three scenarios there, 3A, B, and C. Okay, and we looked at different sort of things, behind the meter with dedicated renewables, power purchase agreements, which people have mentioned today, and also curtailed renewables. Okay, if there is no need for using the renewable energy, let's put it into hydrogen production as well. But the numbers aren't pretty. All right, so if you look at the usage rates, if you look at utilisation rates, pretty low. And then if you look at the levelised cost, it's not great as well going across there. I won't go into too much details. But you can see in here, here's a curve here showing how the current model, NPV, and the proposed model as well. And I'll just rush through this as well. You're welcome to read the report yourself. But there were 3 things that we picked up in this work was that increasing the electrolyser usage rates, having more flexibility in the sourcing of renewable energies, and incorporating diverse sources of renewable generation. These were the things that would improve the viability of hydrogen systems. By the way, the NPV for some of those, none of the NPVs were positive, by the way, and you'll find that it's quite strongly negative in the hundreds of millions to do that. I didn't put the numbers in there at the moment, but you're welcome to read the report. But the key thing I really wanted to get to was this, about the water bit. Okay, and we talk about it as sustainable hydrogen for water utilities, because I've just augmented the diagram out of the white paper and just said, well, what would it look like for the water industry? Okay, and what we found was there's actually, when you use an electrolyser, especially a proton exchange electrolyser, wonderful things appear when you look at it really deeply. You produce a lot of oxygen, okay? And I saw in some diagrams, I think Alfred's diagram, the oxygen's just let off into the air, or Jonathan, you just let it go. But guess what? The water guys have a use for oxygen, all right? And we can't wait for a hydrogen economy, because when you have a hydrogen economy, you're going to have vast amounts of pure oxygen, okay? And pure oxygen is very, very useful for the water people, okay? Really useful stuff, because we can put it into, not only you're producing the hydrogen for your transport and gas and all that sort of stuff, that's the boring bit for the water industry, okay? But that just allows us to get to what we really want, which is the oxygen, because we can use the oxygen in water treatment, okay? The reason why the water industry, or wastewater treatment, is 2% of carbon emissions is because of aeration. We need to oxygenate our treatment plants to keep the biological systems alive, to do all the cleaning up work and allow us to do wonderful things like recycled water, or in Melbourne's case, just dump it in the bay or dump it in Bass Strait. Okay? You spend all this money and CO2, or CO2 emissions, and then you go and dump it. All right, but to do that, we need a lot of oxygen to do that, and that's why in a wastewater treatment plant, 60% of the energy use is actually in one process alone, aeration, pumping air into water to keep the bugs alive. It's a very inefficient process. But and we are using air, and air is only 20% oxygen, if you remember your physics, and the rest is inert material, nitrogen. Okay, so we're pumping a lot of inert material just to get to the oxygen bit. We're burning a lot of energy to do it, but it's cheap. Energy was cheap, and in the 70s and 80s, we were experimenting with more efficient wastewater treatment processes, things that could do things more powerfully, quicker, with pure oxygen. Things work better with pure oxygen, right? Can you imagine biological systems running on pure oxygen, especially bugs? They just go crazy, right? One, the oxygen transfer efficiency, if you know partial gas laws, is a lot higher when you're dealing at a high purity. You can dissolve much more into the water and more efficiently as well. So that's where we come into this picture, all right? And that's where our water utility clients are very, very interested in this, because if they can get their hands on cheap, virtually free, pure oxygen that has no carbon emissions to it, because it's basically you've used electrolysis to do it. And it's going to be cheap because the hydrogen's paid for it, all right? We can put it to use. Don't throw it out in the air. Don't discharge it. Give it to the water industry. We'll put it to good use. Because other areas that we need as we move into the future is ozone generation. Okay? We need ozone generation for treating our drinking water and even disinfecting our wastewater as well. Very useful chemical, ozone, but you need pure oxygen to make it. And the processes that we use to make it on site is either we ship it in, which is pretty expensive, or use some pretty ugly equipment called a vapor pressure swing absorber, right? Mechanically, just a nightmare. The water industry hates them, and that's why we're reluctant to put more ozone generation systems. We can nearly eliminate that whole step. It'll save us only about 25% of the energy, because making ozone is also very energy intensive. But 25% is not a bad saving. But plus, we also don't have to deal with a very problematic piece of mechanical equipment as well to do that. But the other area that we really are drilling down on at the moment is that our biological systems, our ecological systems are under severe stress at the moment, under climate change, all right? You see Menindee Lake, rivers suffering from low oxygen, right, or no oxygen. You're actually seeing areas, big areas, seas basically. I won't give away too much because I'm actually trying to protect confidentiality on some of our clients at the moment. But big seas and big water bodies, like Sydney Harbour sort of type of sizes of water bodies. And they're all running out of oxygen because of our pollution. And to clean up that pollution is going to take too long. And under the climate change scenarios that we think, it's actually going to nuke the actual ecology in those water bodies. Well, guess what? We need a lot of oxygen to actually dissolve back into the environment. We can do it. We've got the technology to do it, but we aren't able to access the purer oxygen to do it. Guess what a hydrogen economy might allow us to do? We could get a lot, and we need a lot. Some water bodies would need 1,000 tonnes per day of pure oxygen. Other water bodies might need 10,000 tonnes a day. All right, we're talking about seas there, because we've got seas that actually go in summertime anoxic and pretty much are dead, which is not a good thing, right? Not only are we going to nuke this planet with CO2, we're going to kill the biology along the way as well, which is not a good thing, by the way. I hope you agree with me. If you don't, we'll talk about that later. All right, so some of the things, the deeper insights, how are we going for time? Couple minutes? Okay, good. I only got a few more slides. Some deeper insights that we got out of this paper, which we couldn't publish because it was just getting a bit too thick, the report. But we really do think we've underestimated the key role water and water utilities will play in this economy, all right? Because I've seen today, Hydrogen Council, with great respect, didn't really focus on the water bit. But here we go, got the water guy talking about it as well. And we think it is unsustainable and inconsistent with a circular economy to be using fresh water, or even groundwater systems that are not renewable, replenishable, all right? And we think a key byproduct, and actually for the water industry, we think that's actually the product, is the pure oxygen, okay? The hydrogen bit's the byproduct, okay? We're not really that caring of it too much. And we can use it in some things, you can put it into the gas networks and biogas systems and all this stuff. And the pure oxygen bit for odour control, so that's another area. So this is where we also eliminate the chemical use in the water industry, because chemicals, as I said before, big carbon footprint. We use a lot of chemicals to control odour, okay? And we got away from using pure oxygen in our sewer networks and all that sort of stuff because it was too expensive. It was actually cheaper to dump chemicals in, like ferric chloride and calcium nitrate, all those sorts of things, to keep our sewers fresh, all right? They just become another electron donor to gobble up all the bad things in the sewer system. But yeah, there you go. We've got a use for this stuff. Man, bring on the hydrogen economy. We love it. And it's very useful. All right, so there's lots of other stuff. I don't want to bore you, but we do think, yep, the transportation sector, great. Okay, that's probably going to be an enabler for us, and we're going to have a wonderful future together. And we also think it's going to be about the livable cities, what I talked about earlier. We really think it's going to help us make these regenerative systems be consistent with what our sewage strategy is telling us, make sure that a circular economy occurs. And we think it does need integration across sectors to do this. So we need to work closely with obviously the hydrogen industrial people, but also with the mobility transportation people. So that's the vision that we can see is happening. And it's going to need that sort of holistic approach to it. I've got about a minute or not? Because I wanted to show some engineering figures today. Am I allowed to do engineering figures? All right, real quick. So this is what we need for say a small wastewater treatment plant, okay, about 5 million litres per day, that's what ADWF is. I have to make it look jargonish and make myself look smart, but I'll try and decipher it for you. But the aeration power to do that is about, 4.7 megawatts per day to do that, or kilowatt hours to do that. And it needs and if we wanted to supply that much oxygen, so the top bit is actually doing it through aeration, right? The bottom bit is how we would do it, through producing hydrogen first. So to get that amount of oxygen at the top there, which is 3,333, okay, kilograms a day, we would need to make about, say, 500 or 400 kilograms a day of hydrogen. That will give us enough oxygen to supply there. But look at the average water consumption there to do that. It's very little. It's only 5,000, 4,000 litres to do that. And the power requirement is quite enormous compared to how we were going to do it. But then we're getting it green, okay? And that's why we can't wait to get for the hydrogen, because it's going to be hard for us to do that by ourselves, okay? But if the oxygen is given to us free, or it's already made as a byproduct, great. And this is sort of the 300 over the side there is a much bigger treatment plant. That would do about half of Melbourne, okay? You would need to double those numbers. It's getting big. These are all the big numbers to do that. So look, I'm going to wrap it up now, but there's some numbers to give you a feel for that. And just one last thing. Bring it on. I want some beer delivered by hydrogen fuel cell trucks, because I reckon that's the best picture ever. All right, thanks a lot, guys.
Well done, John. Thank you also for your patience. I know it's a lot to take in. We only have one more formal presentation to go, but what's good is there is reference to the environmental impetus, and let's never lose sight of why it is that we are pursuing hydrogen economy, hydrogen society, or an emerging hydrogen industry for Australia. So thank you, John, for that. A lot of the presentations tonight have centred on renewable hydrogen. What's fundamental to that is the electrolyser. It's quite evident that we're going to see a massive explosion of electrolyser installations. And what's fundamental to the viability of hydrogen applications is the hydrogen cost derived from an electrolyser. So a fair bit of R&D and testing is going into the area of electrolyser technology. Electrolyser is made up of different materials, sitting at around about $1,000 at the moment. If you look at CSIRO cost curves for electrolysers, we're anticipating significant reductions. But why is that? And the reason why we've asked our next speaker to present is that they've just released a significant paper establishing that some of the new materials they're looking at in terms of what electrolysers are made from present great opportunities for Australians and others to adopt technology which would allow passage for greater hydrogen uptake. Her name is Rosalie Hocking, and I'm very proud to say that I've got to know Rosalie lately, and it's a fantastic start to the introduction of new age materials in electrolyser. So Dr. Rosalie Hocking is a senior lecturer at Swinburne University of Technology. Go these glasses again. Rosalie is a chemist who leads a program studying small molecule transformations at Swinburne University of Technology. Her group uses a range of innovative analytic techniques, including the beamlines of the Australian synchrotron, that's here in Melbourne, assist in new technology development in electrolysers, including those to make hydrogen from water. Rosalie completed her PhD in physical and inorganic chemistry from the University of Sydney in 2004. She has since held positions at Stanford University's Stanford Synchrotron Radiation Laboratory, CSIRO Land and Water, Monash University and James Cook University. She's recently joined Swinburne University of Technology as Vice-Chancellor's Women in STEM Fellow and Senior Lecturer. So please welcome Rosalie to the stage. Thank you. All the best.
Thanks, Luigi. It's been I guess it's a long night, lots of fantastic and different perspectives. I was really thrilled to hear John talk about water, because water is really, really important I actually, when I was at James Cook, I spent a lot of time looking at water and some of the contaminants in water, which is not what I'm going to talk about tonight, but something certainly very dear and close to my heart. A lot of the focus of my career has been on the design of materials through characterisation. It's really sometimes very hard to figure out. We sometimes have a vision of what we want to achieve, but if we want to, sometimes we don't know the nuts and bolts of how to do it. And it's by characterising things that we can often figure that out, which is where I come into that. As an academic scientist, one of the first places we have to start is to ask, what vision is it that we want to achieve? What is it we want to do? And actually sometimes, like, to be honest, there's a big disconnect between academic research and industrial research, and we really, particularly at Swinburne, want to try and bridge that gap. So where I get it wrong, please come and talk to me, help us solve your problems, because it's something we're really passionate about and really something we really want to do. Luigi actually asked me to talk about a particular academic paper, and I'll touch on that a little bit, but I thought perhaps what might be more interesting would be just to talk to you a little bit about some of the innovations we get from the synchrotron. Key to understanding that particular material was actually probing it with synchrotron light. So why on earth would you want to probe a catalyst or a working electrolyser with synchrotron light, and why would you want to do that? And in fact, we look at all sorts of technologies with synchrotron light, not just electrolysers. I've looked at fuel cell technologies, I've looked at batteries, I've looked at lots of different materials where we have questions and problems. Why does a fuel cell stop working after 5 days? Can we use something other than platinum for it? Because platinum sucks as a material because it's so expensive. How do we begin to understand our materials so we can make critical innovations such that industry can make things cheaper? You know, we're here talking about hydrogen, and the last speaker was talking a lot about oxygen, and I actually hadn't thought about how valuable oxygen is so I've taught sewage treatment, so I've thought about oxygen in sewage treatment, but I've never thought about it as having a commodity value in the way you spoke about it. But I have of recent times, and we've started a few projects where we thought, well, if we're going to make hydrogen, maybe we should make something that's got some commodity value on the other side. And actually oxygen wasn't the first thing on my mind because we already do that. So, you know, actually we've started to think about other things that we might be able to make and sell that actually might start to bring down the costs of those electrolysers. So if you can start to make some of those other commodity chemical products, then you can start to think about how you might bring down some of those electrolyser prices. We've spoken about the chemicals industry. I'm in wholehearted agreement. We have a society that relies on the chemical industry, and they are really, really big polluters in terms of CO2. So if we're going to replace those processes, we have to ask ourselves how we're going to do it. And I actually don't know the answers to those questions, but I think those are very important questions. And electrolysers is one part of that solution, but not the only solution to that. We've got to think about our high pressure, high temperature setups that, you know, where you can bring things together with renewable derived temperature, with renewable derived electricity. And all of these things are innovation through characterisation. I also want to touch on metal refining. I think metal refining is an important opportunity for Australia in terms of taking sunlight and putting it somewhere where you've got some commodity value. There are existing markets in metals. So it's just something to keep in mind. So how do we translate vision to reality? And this is a question for us all. We need to be able to make devices that actually work, and that's one of the first questions we need to be able to answer. And then we have practical considerations, commodity value, commodity markets, and key to all of this is understanding how materials work. So why would you use a synchrotron? In fact, a large number of the papers in Australia, and I'd probably guesstimate it's probably like 80% when you get a high-profile paper in Science or Nature about some new innovative technology, whether it's a fuel cell or an electrolyser, often uses a synchrotron. So why is that? So synchrotrons, the joke is, well, we always said the particle physicists invented them because they were studying quarks and leptons, but that's got nothing to do with why we built one in Australia. When I was at Stanford, my boss said, the physicists were working on the synchrotron, so we poked a hole in the side of it to do our characterisation experiment, and they poked the X-rays out the other end, and they started to study protein crystallography. And from there, a new set of innovative techniques were developed. To take a step back from that, actually, I might just skip ahead a little bit because we're sort of running out of time. A lot of the things we know as scientists about matter and materials come from how light interacts with them. So one of the classical ways I tell people, you know, when I'm teaching first year chemistry is to say, well, you've got a pink solution and a blue solution. So you've got a pink solution and a blue solution. So, you know, what are you seeing there? You're seeing how visible light interacts with those materials. But one of the problems we have when we want to study a functional electrolyser or a fuel cell is that the pink solution and the blue solution is not going to cut it, most of the time the real things we want to study, they're complex multi-component materials. So how do you get to the bottom of that? Well, synchrotrons have some advantages. They're basically sources of light, but they're sources of really, really intense light that's got a lot of properties that make them really, really useful for homing in on different components of materials. Some people talk about them as being microscopes on steroids. They basically give us access to techniques that enable us to home in on different components of materials. So just to kind of give you some reference for how light interacts with matter and why it's important, there's a couple of classical examples. Like everybody these days knows what the structure of DNA is, right? Yeah, but you don't pause to think about how they figured that out. Oh, we don't know exactly, but you know it kind of has a double helix and whatever. But importantly, how did they know that? Where did that information come from? So it's kind of the same thing if you want to understand an electrolyser, you need a technique that enables you to home in on the materials in the electrolyser. It's the same thing with imaging. So, most people have had an X-ray. I mean, and probably you can think about, you've got bones that are more dense and so you get a contrast. But again, these days with more innovations in light, we get more contrast and it enables us to get more information. So what are the challenges in this space? And forgive me for skipping ahead a bit, but I think you're sort of all, I do enough lecturing to realise when people are kind of getting to the point they've had enough. So if I was to put up the basic science of an electrolyser, you've got an anode and a cathode, and often you've got a material on there. So that material is basically, it's a catalyst. It's something that enables you to direct those solar-derived or wind-derived electrons and put them someplace you want them to go. So if you want to make hydrogen, you want your H+, your protons, to go to hydrogen, okay? But actually, if you want to make something other than protons, which is actually a pretty big challenge in the research community at the moment, because if you could make other things like acetylene, there's a bit more commodity value to putting your electrons into something like that than hydrogen, for example. Not that we've really been able to do that with make huge amounts of it. You can put the electrons into something that has some commodity value, then you're able to actually start to engineer new devices. So how do you do this? In order to do this, you need to design materials that selectively direct those hydrogens. So there's a lot of questions around the development of these materials. How do we get them to show those sorts of selectivities? How do we study them? And then I guess if you want to do that and you want to look at it in a system, you don't want to just look at a pink solution and a blue solution. Ideally, what you want to do is you want to look at the electrolyser with its potential applied and actually look at it while it's happening so you can understand what's going on in the material. And those are some things that we've been able to do with the Australian synchrotron. And I thought a little bit about the story I would try and tell you tonight, and one of the simplest places I can begin, this is really the first paper I wrote on hydrogen, and actually in my area in inorganic chemistry, that's largely what I teach, one of the big ticket questions people have, and it's still actually a big ticket question, is people go, how does photosynthesis work? Photosynthesis is this really funky process. It takes in oxygen and spits out oxygen and glucose. It's a really useful chemical reaction. We can take in CO2 and split out glucose. Wouldn't that be a great reaction if we could do it? And so actually it would be a really great reaction if we could do it, if we could actually take in CO2 and spit out glucose like photosynthesis does. We'd solve a lot of the world's problems in reality. Photosynthesis is composed of two parts. There's the part that does water oxidation, which is actually the same thing you find in an electrolyser, and there's the part that does the CO2 reduction. So in the early days of these things, there was a lot of thought that one of the best ways to do the water oxidation part might be to simply mimic the biology. And so there was a huge amount of work done on that all around the world. Lots and lots of people did it. And one of the best systems that had come up with, and keep in mind this was a decade ago, we've improved a lot since then, was to take this molecular compound and put it into a polymer film. And it was done by a couple of guys from Monash University. But they didn't really understand how the material worked. And so actually when I first took the position at Monash, I thought, oh, it's a really interesting material. I'd really like to actually figure out how it's really working. Because I knew these materials weren't terribly stable. So I took my electrodes, which is the same thing in anodes and cathodes, and fabricated and had a bit of a look at them at the synchrotron. So we basically made these materials, which are literally real electrodes with real material on them, and put them in front of the beamline and had a look at what went on. We looked at them both ex situ and in situ, meaning we looked at the electrodes after we'd fabricated them, or we'd looked at them on the beamline. And one of the really, really interesting things we found in those systems was that actually, even though you started with a molecular system because you wanted to emulate photosynthesis, it turned out that the material that was actually active in that system was just a really simple component of it. It was just a metal oxide. And we could actually take that metal oxide and then deposit it, very large amounts of it, onto electrodes and make much, much better electrolyte. We could actually make really quite functional electrolyzers out of it. So it was a really, really interesting story. And it was an interesting story from both the electrolyzer development and from the evolutionary perspective, because the material that we found was already something that existed in nature anyway. So it was quite a really, really simple manganese oxide structure. And if anyone here works in alkaline electrolyzers, it actually has exactly the same structure as the benchmark nickel iron oxide electrolyzers, but it occurs in nature. So quite an interesting story from that perspective. And I'm very aware of time. So we were able to take those innovations, and literally what we would do is we would take our electrode, put X-rays, put electrons, and really enable us to learn what's going on. And then usually, as the characterisation specialist, I work with guys fabricating electrodes. So I tend to go, guys, I can see this bit, I can see this bit's changing electrochemically. Why don't you make more of that and we'll see if we can improve it. And we did a lot of that sort of work when I was at Monash. The guys at Monash were able to actually take that metal oxide that I found and then make some deposition processes to make it much, much better. Again, work we did maybe 8 years ago. I wanted to just come back to a couple of studies that have done much more recently. So these two just came out last year. One was the study Luigi referred to, and this one is one I was working on with Monash University. So if you're in the electrolyser space, you'll be aware that most alkaline electrolysers work in base. They need to be basic. The guys at Monash had a fantastic new material because it worked in acid. So this is really important from a design perspective, because if you're in acid, you can make hydrogen much more easily. So there's a lot of energy to actually make hydrogen. And I don't know, I teach first year chemistry, so forgive me, but just by Le Chatelier's principle, if it's more acidic, you make more hydrogen. So it's quite an innovative process. So of course they had one of the problems that's typically presented to me as the person who's in the characterisation business. They're like, Rosalie, we've got this catalyst, but we don't know what it is. How do we figure that out? So one of the things, I work with these guys to actually design an experiment that helps them figure out what their material is. Now, when I say they don't know what it is, I'm probably paraphrasing a bit and get shot down. They knew it was a cobalt, lead, iron oxide, but they didn't know how the different components stuck together. So actually, by using the synchrotron, we can home in and learn how those different components stick together. And in this case, we know that this material is of the type on the left. But actually, I've also seen electrolysers where they work by the type on the right. And I've seen materials break down in fuel cells because of phenomena like what's on the right as well. So by actually learning about these things, we can design new processes. The final study I'll point to is the one from New South Wales that Luigi was referring to. So this is a really, really exciting development. So I started off this talk showing you an anode and cathode. You've got an anode and a cathode, okay, and they're separated. Most commercial electrolysers, when you make an anode and cathode, they're separated. And actually a lot of our efficiencies are lost and gained in that separation. If they're really far apart, you lose a lot of efficiency. So one of the really innovative things these guys did was they stuck them together. So there was no space between them. So actually, again, my part was, how does that interface work? How does it work in the space between the materials? And so we spent quite a lot of time trying to actually sort out what was going on in the middle that enabled that material to work. So that's still very much a fundamental study, but a very different way of designing an electrolyser, because, as I said, instead of separating the anode and cathode, they've called them Janus nanoparticles after sort of symmetrical things, but you've got component of each on both sides of the same material. And so by putting those two things together, you actually find a new way where you could optimise your material. My conclusions, and I'm sorry for bringing my talk a bit faster than maybe I should have, but there are a lot of new exciting developments in electrolyser technologies. We see a lot of new innovative analytical approaches to solving problems. The synchrotron can help us understand how materials work. So, as I said, if you've got devices that start working and stop working, maybe it's a good place to actually try and figure out what's going on so you can actually innovate and get around that roadblock. But I also think that we do have some barriers too that I haven't really mentioned, but there's a lot of barriers between academic research and translating some of those things through too. And we also all need to find more ways to work together between, help get industry to inform us and help us direct some of our academic research so it best helps industry in terms of the translating of new processes. And I'm really happy to talk to people afterwards if you'd like to talk to me more about some of this work. Okay, thank you.
Australian science is world class. For our international guests, we've got some of the best scientists going around, and material science is really where it's at when it comes to hydrogen, be it the materials involved with hydrogen storage, be it the membranes of a fuel cell or an electrolyser. Australians are at the leading edge, and we're very proud of Rosalie and every other, quite a number of scientists here today from a number of universities based here in Melbourne. So very, very proud of your achievements, and we're fully supportive of you, Rosalie. Okay, because we've run out of time, I won't have time to run through the results of the surveys, and thank you for those people that took the effort to report to us on their views on a range of different questions. I assume that people would be interested in receiving those. So we'll accelerate straight into the Q&A session. So perhaps stand up, have a bit of a shake out if you want to, whilst we assemble the panel. So I would, whilst they are taking their seats, the speakers, please take your seats. I might just introduce the two additional panellists. They are Dr. John Soderbaum, the Director of Science and Technology at AIE Allen Consulting. John is a scientist with over 35 years of policy and program experience. His work includes energy, climate change, R&D, innovation and industry development. John works at the interface of the public, private and research sectors and believes collaboration between all these sectors is an important driver of innovation and productivity. I just ask for people just to stand, please. Prior to joining AIE Allen Consulting, he held senior positions in various Commonwealth departments and International Energy Agency. John has played a significant role in several hydrogen-related projects, including the National Hydrogen Study, a report for ARENA on hydrogen export opportunities, the South Australian Government's Green Hydrogen Study, and 2 reports for the National Hydrogen Strategy Task Force, Injection of Hydrogen into Natural Gas Networks Issues Paper, and report on support of on-grid and off-grid electricity systems. John is a Fellow of the Australian Academy of Technological Sciences and Engineering and Vice Chair of its Energy Forum. He has a Bachelor of Science First Class Honours from the University of WA and PhD from the Australian National University. Please welcome John. And lastly, Dr. John Tregonning, Chairman of ETR. After completing a PhD in theoretical physics and a period in research, Ken began working in the energy industry in Europe in 1981. Initially, he worked for Shell in the Netherlands and on secondment to Maersk in Denmark. Prior to undertaking 20 years in consulting, his experience spans much of the global energy sector in corporate and project management, asset evaluation, engineering and financing of projects. Ken has lived and worked in Europe, UK, Australia and Southeast Asia, as well as done business in the USA, India and Central Asia. Initially focused on the upstream oil and gas industry, Ken has been active in the solar electricity industry for the past 5 years. He has co-founded and run companies including 2 mid-sized ASX-listed companies and unlisted solar development company, Emergent Technologies Resources, ETR for short. ETR has large solar electric projects in Australia as well as a project for conversion of renewable energy to a transportable hydrogen carrier. So please join with me in welcoming Ken to the panel. So what we'll do here, Francesco Chiravolo, say hello to Francesco, is going to pass around a microphone if anybody had any questions for any of our panellists tonight. Does anybody have a question? Or do I have to refer to what was in the surveys? Francesco? Yep. Just please introduce who you are and let's try to stimulate a robust discussion.
Stuart Nesbitt, Moreland City Council. My question's to Alfred. In your table, when you looked at the price parity, hydrogen versus diesel, did that assume no carbon price?
Oh, I have to look that up. I actually don't know the answer to that. Apologize. That's a good question, though.
I assumed it did because it's impossible to actually predict whether there's actually going to be one or what it's going to be. But
yeah, that's right. There were some references to
For
that.
the council study, because we showed different studies, for the council studies, there is a $50 per ton.
Oh, that's right, which we thought, many members thought was underestimated because we thought it could be as high as 200. You're right, yeah.
Any other questions? Yes, up the back here. When I get my questions, I might interject.
I remember there was a debate on what number?
Thanks. Colin Long from Victorian Trades Hall Council. One question about water. Is desalinated water entirely useful, or is there a cost issue with that would make it prohibitive? And now I'm entirely going to forget the second question, which is pretty good. Why don't you answer that and I'll think.
You can, as Jonathan was saying, desalinated water, groundwater, any water, it's only about 1 or at the most 2%, 1% of the cost. Most of the cost is in two things, the energy and the cost of electrolyzers as well. But I think what I was trying to say is that we've got other sources of water to use, and desal is obviously not the cheapest source of water and takes a lot of energy to do that. Also produces a lot of residuals as well, which we tend to dump out in the sea as well. So yeah, look, since we're dumping it out in the sea already, let's use some recycled water. It's there. We spend a lot of money to produce it and then to just discharge it. It's a pretty sad state of affairs.
And I do remember the second question, which was about the feasibility of offshore wind as an electricity resource for hydrogen in Australia. We don't have any offshore wind yet, but there are proposals for it, of course, and it would seem like a much more reliable source of energy for a start than solar, and even solar with batteries potentially.
One of the advantages of Australia is because we've got a lot of land area too. So, I mean, a lot of the places that are going for offshore wind are countries that are quite small and haven't got a lot of space to put up wind turbines. Once you've filled a country with wind turbines, you need to find somewhere else to put them. It's possible we may get to the point we do that, but we've still got a lot of coastline to go.
I'd probably just pick up on the word reliability there as well, because I actually think solar is fairly reliable as a power source. We have a pretty good idea over the course of a day ahead of time or over the course of a month or a year about what it's going to do. The problem is the intermittency, and we need storage in order to solve that. The intermittency is it's essentially a cost problem. It's not really a reliability problem, and I think offshore wind is costly in its own ways. You know, it's not cheap to install things in the ocean, and it's not cheap to maintain them. So I think certainly you can get a much better capacity factor out of offshore wind, but you know, I'm not sure that it quite stacks up to Australian solar in terms of a levelised cost of energy just yet.
I might just add that in the context of solar, Australia could effectively be the Saudi Arabia of solar energy, both because we're the most irradiated continent on the Earth, but also the land we have available that's not otherwise used. And all of Australia's energy needs could be met with solar in an area about the size of Canberra. So there's a tremendous resource there that's still underutilised, and that's in part due to the transmission and transportation problems. It's a better use than it's currently employed for, I guess, yeah.
Which bit?
Hang on.
Take it easy, take it easy.
We're not all in the Canberra bubble.
Maybe I'll just also take up with Jonathan's comment about the siting project, the study. I think one of the things that came out of our work for the white paper was that it's surprising, and because I'm a water person, it's surprising where you put wastewater treatment plants. Very, very surprising. They tend to be on large transport corridors, very close to them, and they also need near gas transmission lines as well, most of them. And they also are probably got good access to renewable energy, either through biogas systems, plenty of land for dedicated solar if you want that as well. And I think the transition might be PPAs through the network system as well. But wow, very, very surprising to find your great source of water, and it's right next to where customers, mobility customers are. It's incredible. Yeah, go and map it.
In the pause, I should just make clear the energy I was referring to was electricity.
Question. Erwin has touched base on sort of the three important steps of bringing this hydrogen economy in place: mobility markets, and industrial hubs, as well as the activation of international export. But in terms of what we've spoken about and what's known as the challenges of bringing hydrogen into the market, it's to make hydrogen sort of reliably, we need a large volume. The challenge is bringing it into a small volume. So getting the efficiency, getting in the systems design, the amount of hydrogen produced, all those factors kind of push towards large-scale hydrogen production at localized or decentralized stations, rather feeding a sort of larger demand than smaller demand. So how do we, and it's also more demand to use for, trucks and industries and heating and all that stuff than because the mobility market is just a third of the entire sort of use of energy. So wouldn't it make more sense to deliver a large scale for industry before a sort of a level of the private client sort of vehicles or smaller scale in terms of hydrogen systems?
Yes. I will have two reasons for this. One is probably the graph that was shown by Alfred, showing what is the break-even cost of hydrogen in order to penetrate these markets in relation with the incumbent solution. And indeed, you see especially heavy-duty mobility was there at the beginning. You're right that light-duty vehicles were probably far more on the right side. But mobility is more accessible than industry in general from this respect. Second is that you need to have a regulation framework or an industry drive into this direction to make things happen. We have been advocating in a number of places so that some industries start going into this way, replacing grey hydrogen by low carbon hydrogen. But as long as there is not a regulation in place, it's very difficult to make things really happen and get momentum. Whereas in the mobility sector, even if it's not always regulated already, we've seen in heavy duty, for example, 2030 in Europe, there is a very clear binding direction. But even if it's not regulated, OEMs have acknowledged that there will be a powertrain revolution. So it's moving, and this gives enough drive for them to work on it and the entire ecosystem to work on it. So again, it's an alignment of all the different parties involved that it is in this direction, and then you can make things moving. But beyond this, you're right. It would be it would make a lot of sense to start by industry, but this is the reason why it has started by mobility. And now I think we are at a stage where probably the two are going to progress in parallel. But we should still, if we look at the microscope the next 10 years, we should still see the volumes ramping up on mobility a bit earlier, and that will be useful for upstream investments.
Yes, thanks everyone for your presentations. They were really insightful. Just a quick question when it comes to sustainability with this transition to a renewable, I guess, energy and technology. We'll need to produce a lot of new infrastructure, a lot of solar panels, batteries, and I guess with the mobility side of it, which was touched on in the discussions, I guess a lot of new fleets of vehicles, trucks, trains.
Don't hear you very well. Sorry.
The green is on.
Yeah.
Oh, sorry, can you hear me?
Yeah.
Oh, there we go. Sorry. I was just touching on sustainability with the transition to a renewable energy economy and technologies. So specifically with things like having to build a lot more batteries or build batteries, solar panels, particularly with mobility as well, building new fleets of vehicles, trucks. Is with the hydrogen fuel cell and the technology, is there much research being done into, say, adapting the technology and retrofitting in existing vehicles, trains, etc.?
Yeah, maybe I'll look at give you my perspective from a fuel cell angle. So, the question on sustainability, it's a good one. In fact, it's kind of forward-looking to part 2 of a paper that we're about to publish with Deloitte on this particular topic, and in particular to look at fuel cell battery electric vehicles, fuel cell electric vehicles versus battery electric vehicles, and in fuel cells, we see some really steep opportunities for some steep cost reduction because we don't have the exotic materials that are going into some of the into the products that we build. So in batteries, the lithium gets talked about a lot, but what's not talked about is the cobalt and other exotic materials, and that makes things a lot less scalable. Like it's really linear, Like if you talk like in battery technology, we're really kind of reaching the end of how much cost reduction you can get because of these type of materials, both from a supply perspective and from a cost perspective. We don't have that limitation on the fuel cell side because it's mostly metal, steel, aluminum, and other pieces other than platinum that we have. So this is one that we're going to be touching on a little bit more in the second part of our series. So maybe that's something that you guys can keep an eye on.
We certainly will. Probably time for maybe 2 more. Francesca, I'll leave it up to you. Just introduce yourself. Yep.
Yeah, hi, Neil Pollock from DNVGL. Very quick question about how you can balance like a short-term opportunity to use SMR, which is obviously publicly not particularly welcome, or even worse with using the coal gasification, to how you can then get, particularly over the next 10 to 15 years where the cost competitiveness of electrolysis comes in. How do we make the jumps now, knowing that then we're committing to some other things that aren't going to be as publicly popular?
Just to be clear about the question, is there still a future for SMR, or is it difficult to justify further optimization work on SMR because after 20 years electrolysis is coming?
I guess I'm coming from the background. We're working on a project in the UK where we know initially we're set up with SMR, and then we know that we will move then on to offshore wind-powered electrolysis. But we've got to wait for that to become cost-effective. So in the meantime, you've got to make the jump. You've got to get everything going using the SMR so that you can then start to, this is for decarbonising heat, to use that. Okay. And we're all talking about 10 years, but we need to make jumps.
The future of SMR is linked to the future of CCS and biogas. So countries where you will have biogas, you will be able to still invest new SMR, or you'll put biogas in existing SMR. And if CCS, but by the way, even CCU gets widely developed, SMR will remain a very relevant technology. So I think for the next 20, 30 years, that's a technology that we will keep seeing in parallel of electrolysis. That's very clear.
I might just make a quick comment, following up on a discussion we actually had before, I had with Erwin, about carbon capture and storage. I come from an industry which is the drilling industry. So I'd spent many years in oil and gas, including quite a bit of time involved in drilling, but also looking at economics and so on. There are very special conditions to have carbon capture and storage work, and I don't see anywhere in the world those conditions could work on the scale needed. The only places in the world carbon capture and storage has worked is where the CO2 is used for enhanced recovery of oil in an existing oil field, which has been depleted. So there's some very special conditions, even just to store carbon dioxide, because it's got some very strange rheological properties. It doesn't behave just that you compress it and you give it and you push it down a hole. It's much more complicated than that. So I actually am very dubious about the viability long-term of any carbon capture and storage concepts.
There may be some conflicting views on this. I think the jury's out, isn't it?
I am talking only from my own experience.
I'm not trying to disagree with you, Ken, but I'm sure that there's a broad range of
I'm sure there are many
views. Did anybody want to comment on that? Jeremy? No.
I don't want to comment on the carbon capture side of things. I sort of want to come back to
leave that for another day, Jonathan.
I don't know anything about it.
I'll take that as a win.
Well, this is fundamental, though, isn't it? That we don't really know about it. We might run an event on CCS. I'm pushing it through the committee, actually. But yeah, go on, Jonathan. Yeah.
I guess in terms of the question of SMR as a transition, I think it's, for some applications it might be necessary, but particularly for applications where you're not really sure if hydrogen is right for your application and you want to have a bit of a cooling off period, I suppose. You don't want to go and build yourself a whole electrolysis facility only to find that it's, you know, giving you terrible returns on investment. I would say the cost reductions we're seeking in green hydrogen or sustainable hydrogen or zero carbon hydrogen, we're not going to get them unless we ramp up electrolyzed hydrogen production specifically. And I think governments are aware that that's kind of one of the key problems that need to be solved, and I think there's an increasing appetite to subsidise and contribute, incentivise electrolyzed hydrogen production. So I would say if it's a specific project you're talking about, work really hard to try and get some government funding to do an electrolysis plant rather than using SMR for the moment, because it may just be that you can get it.
Okay. I think I'm going to draw it to a close there. I'll take this opportunity to thank all of our speakers and panellists, and apologies for rushing through the agenda. I might pose a question to the floor. Would an event on carbon capture and storage be of interest to our members and non-members here today? Should we push that through the committee? I think it does. I think it's something that's on my mind, and I guess on a lot of other people's. So we will do that. And also thank you for all indicating we've got a 100% strike rate that the AIE should pursue the idea of running more hydrogen events. So there's about 42 people that returned surveys, and all of them, 100%, indicated an interest. So we'll certainly investigate that in conjunction with CADEM's committee, and look forward to seeing you at the next event. But before that, we'd like to acknowledge the participation and the tremendous presentations from our speakers and the contributions of our two panellists, even though John Soderbaum had to nick off pretty quickly. So we've got some small gifts, so as we call your name, just come and receive a token gesture of our appreciation. Erwin, Perdenfornis, come forward. Get in.
Oh, I think he's calling for you.
Just do it all. Just give. Thank you very much. Thank you. Alfred Wong. Just give them. Yeah, all right. I think we're just going to give them. A lot quicker. Sorry for rushing. Yeah, one each.
Thanks.
Thank you.
Rosalie.
Thank you.
Ken, for you. It's a bottle. We've also got one small special gift for a person that worked tirelessly, not on our committee, but representing Arup. And that's Abby Roberts. If she could come to the stage, if she's still around. She's still here. Yeah, she is. She's coming slowly. Come forward. Yes, go on. These events are impossible without the likes of Abby and her team. We're very grateful to Arup for having us here tonight. I would encourage you all to hang around till we've got the venue till 9 o'clock. If that's the one. And mingle. Good on you. Thanks a lot. Well done. You enjoyed that, the Chardonnay. Thank you also to Cadem and the committee for allowing me to run this event. I hope that you've thoroughly enjoyed it. Please stick around. Like I said, we've got the venue till 9 and we'll see you at the next AIE event. Thank you. No worries. Thanks for being here.